Okay, so in this lesson, we're going to talk about three things. We're going to look at the domain of a log function. And remember, the domain is a set of x coordinates. And we're going to look at common logarithms and natural logarithms. With regards to the domain, remember in the last lesson we talked about the fact that x here must be greater than 0. All right, so we stated that when you take the log of a number, that number x, that argument, must be positive. Okay, so if you take your calculator just for a moment without even knowing what you're doing, just let's find the log of, let's say, 3. So if I take the log of 3, so on your calculator, you're going to, the log button is, let's see, right here. All right, see right here? That's your log button. So press LOG, and then press 3, close the parentheses, press equal, and so the log of 3 is approximately 0.477, let's say. So let's say approximately 0.477. But what if I take the log of a negative 3? The log of a negative 3. So let's see. So if I take the log of a negative 3, close parentheses, notice I get an error. Okay, I get a domain error. So I get an error here. So the log of a negative 3 does not exist. Does not exist. It's not a real number. Okay, so not a real number. All right. So whenever I take the log of a number, that number must be positive. Even taking the log of 0. So if you take the log of 0, to the log of 0, log base log of 0 rather, notice you get domain error also. All right, so that's not a real number. Okay, so you don't get a real number. Now let's kind of determine why that's true. Okay, so let's look at something similar to this. Let's see why the domain must be a positive number only. So let's look at this. Suppose I wanted to say, let's find the log of 2, base 2 rather, of, let's say, negative 8. Okay, and so to find out what this is, remember we did to evaluate this log expression without using a calculator, we kind of changed this to an exponential equation. So we said 2 to what power is a negative 8. All right, so that was a question. Well, remember the base is 2. It's positive. So positive number raised to any power is always going to be positive. It's never going to be negative. This is never negative. Okay, so 2 to a power is either 0 or positive. So that's why that's why the argument can be negative. So the argument can never be negative because this doesn't make any sense. 2 to no power, 2 to a power is, that power does not exist. It's never going to be negative. 2 to a power is always going to be either 0, I'm sorry, I didn't mean 0. I did not mean that. So it's either going to be, it's going to be positive. Okay, so 2 to a power is either, it is going to be positive, is positive. All right, so what I meant by 0 was 2 to the 0 power is 1. So that's still positive. And 2 to a negative 1 power is 1/2. So that's still positive. 2 to the 3rd power is 8. That's still positive. Okay, so 2 to a power, regardless of what that power is, what that exponent is, if it's 0, negative, positive exponent, it's always going to be a positive number. Okay, and it's never going to be 0 either. So it's not going to be negative, it's not going to be 0. Okay, all right, now, so let's find the domain of this expression. Find the domain of this expression. So let's see. Number 1, find the domain. Now this is going to be important when we start graphing these because the domain is going to help us with what's called a vertical asymptote. remember the exponential had a horizontal asymptote? The logarithm is going to have a vertical asymptote when we graph. But we're not going to graph in this lesson. So find the domain of each log function. All right, suppose we had this. Suppose we had f of x is log base 6 of x plus 4. Okay, so, oops, this might, yeah, it'll be fine. Log base 6 of x plus 4. Okay, so it doesn't matter what the base is. The base could have been 60, the base could have been 2. It does not matter. I can only, to find the domain though, I'm trying to find out what this argument needs to be. Because remember, I can only take the log of a positive number. So the argument, just like right here, the argument, remember, we said, this is the argument, so we said that this argument must be positive, must be greater than 0. So what we do is we take the argument and we set it greater than 0. We solve this inequality. So we're going to solve this inequality. And that's going to give us our domain. So once we get x by itself, that's our answer. So we subtract 4 from both sides, and so I get x is greater than negative 4. All right, but then they're going to ask you to write this as interval notation. So the domain in interval notation will be, remember there's no equal sign here. So because it cannot equal 0. Remember, the argument cannot be 0. It must be strictly greater than 0. So you're going to say parentheses negative 4 to infinity because it says greater than. Okay? So remember, don't make the mistake and say x plus 4 is greater equal to 0 because notice the argument must be strictly bigger than 0. This can never be 0. Cannot be negative and cannot be 0 either. Okay, so kind of like if we went back here, the log of 0 base 2. So let's see if this makes sense. Is it possible to take the log of 0 base 2? Well, 2 to what power is 0? There isn't any. 2 to no power is ever going to be 0. That's not possible. Okay? So this does not exist. All right, it's not possible. All right, so it's strictly greater than 0. So that's the domain. And then B, so it's very easy to find the domain. Let's suppose f of x this time is log base 2 of x minus 5. So again, you take the argument. So this must be a positive number. So we say x minus 5 must be greater than 0. And then you solve this linear inequality. So you add 5 to both sides. And so you get x is greater than 5. But as an interval, my domain is going to be parentheses 5 to infinity. Don't make the mistake and say bracket, because if you say bracket, you're saying that this can be 0. That's not possible. Okay, the log of 0 does not exist. You can't take the log of 0. Okay, so that was number 1. That's how you find it. You just take the argument, say greater than 0, and solve for x. And you found your domain. Just make sure in the end that you're going to end up having to write this in interval notation. Okay? Now let's talk about this right here. You remember a while ago I asked you to take the log of 3? Okay, the log of 3, and you found the log of 3 to be, if you recall, that was right here, log of 3. And you found the log of 3 when you took the log of 3. So log of 3. You found that to be 3 decimal places, 0.477. All right. Now, what if you wanted to find the log? Let's see, the log of, let's say 100. Just do that for a moment. The log of 100. So take the log of 100. So say log 100 close equal, and notice this is just a nice whole number 2. Okay? Now what if I did this though? What if I did the log? Now before I go 1, notice I did not put a base here. See, I did not put a base. I did not write a base. Now there's a reason I didn't need a base here, and you'll see why in a little while. Okay, but what if I did this? What if I put the log of 100 base 10? And I said do this without the calculator. Without a calculator. Without a calculator. Alright, so you're going to say equal box. You can change this to an exponential. So 10 to what power is 100? Well, the answer is 10 squared. So that's 2. Alright, well, that's the same thing as this. So this is 2, this is 2. And so the point here is that see this base here is a 10? So there's no base. If there's no base, LOG, if there's no base, my base is understood to be a 10. So this base right here is understood to be a 10. Base is understood to be a 10. Okay? And whenever the base is 10, whenever the base is 10, we are dealing with common logarithms. Okay, so we're dealing with common logarithms. All right, so your calculator uses 2 bases for logarithms, LOG, and we'll talk about this in a little while. That's ln. So LOG. So the 2 common bases. Well, let's talk about the first one. So there are 2 common bases. Let me not use the word common here. So 2 bases used more often are base 10 and base E. Remember the previous lesson we talked about the number E. All right. So base 10 and base C. Okay. So base 10 is going to be called a common logarithm. Okay, base 10 will be called a common logarithm. Base E will be called a natural logarithm. So base 10 will be called a common logarithm, and base E is going to be called a natural logarithm. All right, so if you had log of 8 base 2, and then log of just 8. So here, the base is 2. Here, the base, if there's no base, remember it's understood to be a 10. Here, the base is 10. So this right here is called a common logarithm. And it's called a common logarithm because the base is 10. Because the base is 10. If there's no base, it's understood to be 10. Don't say it's understood to be 1, because that's not true. Because the base can never be 1, remember? The base of a logarithm can never be 1. The base of an exponential can never be 1. It would be any positive number but 1. Okay, so it's called a logarithm because the base is 10. So in your calculator, let's figure out what the log of 8 is approximately equal to. So you just say log of 8, log of 8, closed, equal, so it's about 0.903. Okay? So basically what you found was this. Let me just explain what you found. If you change this to exponential, what you found is this. So you found that 10 raised to the 0.903 is approximately equal to 8. That's what you found. So 10 raised to the 0.903 is approximately equal to 8. So if you had the log, let's say, of 7, let's say 7.2. Log of 7.2, so say log 7.2, close, equal. So that's about 0.857. And so what you found is that remember there's no base there, so it's going to be 10. So what you found is that 10 raised to the 0.857, we said 0.857 is approximately equal to 7.2. That's what you found. And you can check it. So watch, do 10 to the point 857. So you say 10 raised to the 0.857. Hopefully it's about equal to this one. These are all approximations now. And so notice 7.2. If you round off to the nearest 10, 7.2. All right, so there's no base. It's understood to be it's understood to be 10, which is a common logarithm, and your calculator uses base 10. That's the LOG. Okay? Now, let's look at this. Let's suppose I want you to tell me what the log base E of, let's say, E squared is. Log base E of E squared. Okay? So you first of all, remember what you did, was you changed this to an exponential equation. So you said E to what power is the argument, E squared. And so you said the answer was 2. Okay? All right, now, so E squared is 2. Okay, now what if you, so you see the base is E. So when the base is E, we are dealing with natural logarithms. All right, now this is how it's going to look. So log base E of 5, let's say. Log base E is of 5. All right, log base E of 5. Whenever the base is E, we don't write it like this. We do not write it log base E. We don't use that notation. We don't use those symbols. What we do is this. We rewrite it as ln of 5. So you read this as ln of 5. That's how you read it. So ln of 5. Okay, ln of 5. So log base E, whenever the base is E, you're dealing with natural logarithm. So ln of 5. So then you just use your ln button. So when there are two more common bases using mathematics are base 10 and base E in terms of logarithms. Base 10 is a common logarithm, base E is a natural logarithm. So whenever you're taking the ln of 5, you're saying that the base is E. So you have to use the ln button. So you'll say ln, so how it shows up with the natural log of 5, close parentheses, press equal, and that's 1.609. So this is approximately 1.609. Okay? All right, so in this example, let's evaluate each. I'm going to just continue talking about this for a little while. So number 1, so you have the log of 1.6. Log of 1.6, remember that's the common logarithm. The base is understood to be 10. I can use my calculator. So since I can use my calculator, since the base is 10, I'm going to say log 1.6, close the parentheses, press equal, and that's about 0.204. Okay? Number 2, if I have the natural log of 1.6, let's say, natural log of 1.6, so I'm going to get a different answer because this is base 10, whereas this is base E. So 10 to this power is 1.6. E to some different power is going to be 1.6. So let's see. So the natural log of 1.6, and I get 0.470. Okay? All right. So remember, this is common logarithms, this is natural logarithms. This is base 10, this is base E. Okay? All right, so let's look at some examples with this. All right, so the next set of directions is going to say evaluate each, and let's just go ahead and rewrite this over. So evaluate or simplify each expression without using a calculator. Each expression without using a calculator. Okay, number one. The log of 100. All right, so notice there's no base there. There's no base there. It's understood to be a 10. So let's think about this. Just rewrite if you need to. So this in your mind, this is what you're saying. Log base 10 of 100 equals some exponent. So now let's change this to an exponential. 10 to what exponent is 100? So the answer is 2. So 2 goes here. That's your answer. 2. Number 2, let's suppose we had log of 10 to the 7th. All right, so just rewrite it. Don't make it difficult. It's very easy. Just rewrite this with the base 10. So in your mind, you're saying, okay, there's no base there. It's understood to be a 10, so the subscript 10. And then my argument is 10 to the 7th. Now I want to know what is that exponent equal to. That's what I'm asking. 10 to what exponent is this? So 10 to what power is 10 to the 7th? Well, there we go with what we talked about earlier. Whenever the base is the same, the exponents have to be equal. So my exponent has to be a 7. So the answer here is 7. 10 to the 7th power is 10 to the 7th. Number 3, suppose you had the log, let's rewrite it. 10 is the base, and the exponent is the log of 33. Well, that goes back to one of the other rules we had. Remember when we had remember this base right here is going to be 10, so let's think about it like that as well. So that's log base 10 of 33. So whenever the exponent is a log and those bases are the same, remember it's just the argument. So that's just 33. So the answer here is 33. Number 4. Okay, suppose we had now the natural log of 1. All right, I want you to think about this for a moment. For those in your mind, this is what you should be thinking about in your mind. In your mind, remember, the ln really means log base e. That's what it means, log base e. So you may want to rewrite the ln like this. So rewrite this as this now. So the log of 1 base e. So the ln of 1, the natural log of 1, is log of 1 base e. Now I want to find out what that exponent equals to. So in your mind, you're saying e to what power is 1? Well, e to what power is 1? The answer is 0. So the answer here is 0. So e, remember that base is to be e. So e to the 0 power is 1. Number 5. Okay, so number 5, you had the natural log of 1 over e. Actually, let's do this one. And number 5, you have the natural log of e to the 6. Okay, that's e to the 6. All right, so it helps if you rewrite the ln as log of e to the 6 base e. So remember, natural log, the base is understood to be e. So we're trying to figure out what is that exponent equal to. What is this exponent equal to? E to what exponent? E to what exponent is the argument, e to the 6. Well, since the base is the same, the exponents have to be the same, so that has to be 6. So the answer here is 6. That's the answer. Number 6, suppose you had this, what natural log of 1 over e to the 6. Okay, so remember that's where we're going to have to deal with those negative exponents now. Okay, so remember 1 over e to the 6 is the same thing as saying e to the negative 6. So we saw that in the previous lesson. So at some point you're going to want to rewrite this as this. All right, now remember, rewrite ln as log, and now I'm going to go ahead and rewrite 1 over e to the 6 as this. Okay, so log of e to the negative 6. Now remember, you got to rewrite. Don't leave the base off, because if you leave it off, this is understood to be a 10. It's not a 10. That base is e. So you got to say e here. Okay? So don't leave the base off, because if you do, it's understood to be a 10, and that's not what this is. Natural log has base e. Okay, so you're trying to figure out what is this exponent equal to. So you'll say e to what exponent is the argument, e to negative 6. Well, since the base is the same, the exponents have to be the same. So this has to be negative 6, which means this is equal to negative 6. Okay, number 7. Suppose you had this, e to the natural log of 125. Well, that goes back to the same thing we did, let's see if I can find it, same thing we did here, remember? So if the exponential log, look at the bases. If this base is the same as this base, and it is, see right here, that base 10, log with no base is understood to be base 10, then it's just the argument. Well, that's what this is. So remember this right here? Isn't that the same thing as saying e to the log of 125 base e? So log base e means natural log. Well, since the base is the same, the answer is just the argument, 125. There's your answer. All right, 8. You have the natural log of e to the 9x. The natural log of e to the 9x. Again, rewrite ln as log base e, and then your argument's e to the 9x. So you're saying log e to the 9x base e, because remember this part here is that ln. Okay, so think about it like that. All right, now you're trying to figure out what is that exponent equal to. That's what you want to know. So you're going to say e to what exponent is the argument. Well, since the base is the same, the exponents have to be equal. So this becomes 9x, so the answer here is 9x. Okay? All right, so that's going to take care of common logarithms and natural logarithms. Okay, so just remember how we wrote this. So it does help to rewrite just like we did. So rewrite the ln as log base e, and then change it to an exponential, and it does help. It does help you to understand what's going on. Okay, so that takes care of this lesson.